Hey everyone, good evening and welcome to our next live session on YouTube that we have. Quantmasters is taking up these live sessions to make sure that you will be able to clear the interviews for Infosys, TCS Digital, as well as NQT. These are going to be the most common interview questions that we can generally expect when it comes down to TCS Digital or NQT or Infosys as well in terms of coding rounds. So we have already gone through 15, 16 plus hours of these coding rounds, and we're going to continue that today by going through another program that is called string rotation. So good evening to everyone joining in the live chat where we have this interactive session where you guys will be able to chat with me and I'll be able to clear any doubts or questions that you may have. So before we begin, as always, hey guys, I hope everyone's able to hear me, see the screen. You guys can just put in a text if I'm audible and you're able to see the screen. If so, we'll go ahead immediately and begin the session without any delay. All right, perfect. AV check. Everybody can hear me and see the screen. Very glad to know that. Now let's go ahead without any delay and let's go on to our question here. So the question here is that we're working on today is to find if a string is a rotation of another string. So this is the basic idea. So take this scenario. This is our first string. Let's take one more string. I'm just going to revise it very quickly so that we are very clear about this. So this is our second string. Now we know the second string is a valid rotation of first string, but how am I going to figure that out? Our brute force method involved taking each rotation of our first string. So when you take each rotation of our first string, let's say we move n here, and then let's say we move o again. So I'm just going to quickly write all the rotations here. So these are all our rotations of string 1. So what I need to figure out, what we need to figure out, if two strings are given like this, our first string could be any of these. Let's say this is our second string. Now no matter which one is given, second string is a valid rotation of first string, because if I keep taking any one of these strings, and I move one character at a time, at one point of time, I will end up with the second string for sure. This is how we can get to know that second string is a valid rotation of our first string. But what is the best way to figure this out? Because in here, what we have learned in our last session is that in this scenario, let's assume worst case our second string is equal to the last rotation of our first string. In that case, I need to rotate my first string basically n times. Because the length is n, I need to perform n rotations to get n different rotations, or rotate it n times. And for each time, I need to compare it with my string 2. And when I compare, I need to perform n operations. So this n operations to compare n characters is performed n times. So basically, your time complexity here is going to be n times n, which is basically n square. Big O of n square is the time complexity of this program. That's too much for us. That's a huge amount. We want to reduce it. We want to make it linear. We want to make it linear, something like big of n into a constant, like n into n plus a constant, or n into a constant like 1 or 2 or 3 or 4 or something like that. We need to make it much smaller, because if you guys think even like something like 2n or 3n or 4n is significantly lesser than n when n square, when the value of n becomes larger. So that's our main thought. That's what we want to do. So one of the first logic we tried to figure out in order to do this is, if I take my first string, let's say there is rotation, and I append it to itself, that is I type rotation again, it's gonna create a string of length 2n, and all I need to do is search for this substring within it. That's all we need to do. Because if I append the string by itself, it will consist of all the rotations here. My first rotation, second rotation, third rotation, fourth rotation, A to T, fifth rotation, T to A, sixth rotation, I to T, and seventh rotation, O to I. We've got all rotations over here, and eighth rotation, sorry, N to O. All rotations will be here. The only condition is that string 1 initially and string 2 initially must be of same size. As long as they're of same size, I can search for string 2 within string 1 basically anywhere. It really doesn't matter. But even here, the problem is when you perform substring searching, the method isn't really efficient. It's really not a very efficient method. Because if you guys observe this, what we are doing here is searching for second string within first string. I need to compare these two. Then I need to move my second string over here, compare these two. Then I need to move my second string again, over here and compare, let's say, these two. Then again, we need to do some movement over here and like do further on for so many number of times we need to do that. We have to perform that a lot of times. So this becomes very difficult for us to work through. This becomes very difficult for us to like calculate, because here also we are taking n square number of operations. Now I have one question. Please do some questions on linked list and trees. We'll work on them, not to worry. I think we have done a lot in our competitive coding video sections is what we have done, trees and linked list, I think. But we'll see and plan, right? No worries. Now let's take this current program that we have and try to work on this. Now, the first thing I'm just going to point out here, remember, even here, when we use this naive method, when we use this method for string compare, we're gonna still go ahead to have a big O of n square. That is, even here we will have exactly n square time complexity. One of the best ways to solve it, as 051 Mohit exactly pointed out, is KMP algorithm. So KMP algorithm is the one which we're gonna use to solve this exact problem. So I think yesterday I gave a small introduction onto what is that algorithm, how it is and everything. KMP algorithm is created by 3 computer scientists, that is Nutch, Morris and Pratt. So since they created this together, they basically named it under their initials as KMP string or pattern matching, or whatever you may want to call it as algorithm. So this is exactly the algorithm we're going to use. So KMP algorithm is a specialized algorithm which helps us find patterns within a string. And what it does is it tries to reduce the time complexity within your program. It is one of the I would say advanced and the best and most efficient method to find substrings within a string. Now, what I'm going to take here is for us to understand it easily, I'm going to take a special kind of string, because we need repetitions. We need our string to have some repeated values. That is when we get to see different case scenarios. That's why I'm going to use a different string here. I'll take, let's say, a particular string. This is generally what we end up using whenever we learn this. So I'm going to take the same string. All right. So I'll take this particular string. Hold on, guys. Kindly hold on. Let me just try to remember the exact string. So we have this particular string. Let's just take this. We want to search for, let's say, a string called barber or something like that. Like let's say in a lengthy string. And for us to figure it out, for us to figure this out again, I'll just point out there's multiple algorithms. So there's horse pool algorithm, there's KMP algorithm. Just to point out and just to know, just to show everybody, there's tens and tens of algorithms. So this is something I always would say is one of the best things for you guys to work through. One of the best things for you guys to learn through and work through, because it gives you the solution in possibly one of the best, let's say, time complexity to begin with. So I'm just going to take a random example with just A, B, C and stuff like that. Let's just take this simple scenario. I'll take, let's say this is what we take. Again, let's say this is our pattern. Now, why am I taking this particular string instead of rotation? I'll explain. For now, just remember, this is a string matching algorithm. We want to find this is a pattern of string. This pattern we want to find in a lengthy string. We'll have a lengthy string and we want to find this particular pattern in that lengthy string. So let me quickly take up the lengthy string and we'll write it down very quickly over here so that we can find it within it. So I'm gonna take I think A, B. I think I need I think this is good enough. Anything works fine. So let's take this couple of examples and I'll show you guys how it works. See guys, in your typical naive string matching method, we're gonna search for the pattern in the string. If it's not available, we'll move the pattern once. We're gonna search it within the string. If it's not available, we'll move the pattern once. We're gonna search it within the string. If it's not available, again do the same thing. Move the pattern, search within the string. If not available, move the pattern, search within the string. If not available, again move the pattern, search within the string. We need to keep repeating this constantly until the end, because we need to find like, let's say, number of comparisons, number of occurrences or something. In our case, in our example, we don't need to do that, but I'm just showing you guys this in this particular scenario. Now, here's what we need to do. For us to use KMP algorithm, we need to use a special kind of array. We need to create a separate array, which is sometimes called pi array or sometimes called LPS, longest prefix substring. LPS stands for longest prefix substring. So this particular array that we're going to create is sometimes, it depends on which textbook you're going through or which material you're going through. Some call it as pi array, some call it as longest prefix subsequence. I prefer to always call it as longest prefix subsequence because it gives the right meaning towards it. So what we're going to do here is create an array which will help us understand where the starting subsequence of our pattern repeats. Think of this, for example. I'll take a string, let's say hello herb. In the string hello herb, HE is repeating. So this is a prefix. This is a starting part of the string which is repeating somewhere else. So wherever prefixes repeat, I need to mark them separately. Why am I going to mark them? I'll explain that in a while. Now, I'll explain that in a while because it helps our search perform much easier. Now, same way, for this particular string, I need to create my LPS. So let's create our longest subsequence array. Now, just remember, for first character, whatever is the first character, it really doesn't matter. For first character, 0 is the index because it's basically starting with 0. We really don't care about it. It's just starting with 0. Now, let's take a look at B. Is B here is B here a prefix? No, B is not a prefix. Since B is not a prefix, I'm going to write it as 0 as well. Now, is A a prefix? Yes, because A is the first character here. If you guys observe, A is the first character, same thing is repeated here. So, you can say first character is repeated here. So, prefix is repeated. So, wherever prefix, in this case, wherever prefix of your pattern is repeated somewhere else, you need to start making a count for it. Now, don't get too confused if it's slightly difficult. Why do we need to do this and everything? Once I'll take an example, you'll have a really good idea. You'll have a really good understanding on how this works. Now, take this for instance. Since prefix is starting from A, I'll keep it to 1. Now, is prefix continuing here? Let's take a look at this. AB is the first two characters. Is the prefix continuing here? Are we having a copy of the prefix here from A and B? Yes, we are. We do have a copy of the prefix. Since prefix is basically copied over here, I'm just going to continue the numbers. I'm going to have to continue the numbers from 1 to 2 likewise. Now, let me ask you guys, these are the first three characters, A, B, A. Is the prefix continuing here? What do you think? Do you guys think the prefix is continuing in this case? The first three characters are ABA. Same ABA I'm finding in middle also, right? So the prefix characters are continuing. Since prefix characters are continuing, I can say this A is the third character of my prefix. Now, what about C? Is C available anywhere before? Is C available as a next character in the prefix? No, it's not available as the next character. Is it the first character of my pattern? No, it's not the first character either. Either our prefix should continue or it should start from first character. If neither of this happens, we will set it to 0. What should I add to A now? If you guys observe till here, you guys might have gotten a good idea of this. You guys might have gotten a good idea of how this program works. So what do you think I should add at the end? This is where I'm asking you guys to let me know. Think about it once. So I'm getting a few different answers. Some are saying 1, some are saying 4. Okay. It is the first character, right? Because it's starting from here. Our prefix is starting from here. C was no longer there. Our prefix was from A, B and A was there. So we found A, B and A. After A, B and A, what is there? B is there. Here after A, B and A, did we get B? No. Since we didn't get B, we are cancelling and writing 0. Now, we are starting a new prefix. This is one more prefix repetition that we are finding. This was the prefix where we had one more prefix we are repeating here. So logically, yes, we would think that since numbers are increasing, we may go to 4. That's a logically correct answer as well. But we want to find wherever prefixes exist as a new set of prefixes. So this is one set of prefix. This is another set of prefix. So I'm going to have to start this with 1 as well. So this here is our longest prefix subsequence. This is our LPS array. Once we have this LPS array, we can go ahead and create this. Now, is the idea of LPS array clear for everyone, or do you guys want me to take one more example to understand LPS? You guys can let me know if you want me to go through one more little example to understand LPS better. We can take one more example where I can show you guys how to calculate LPS over here. Alright, take one more, no problems, we'll do that. Alright, now take, for instance, this is our, okay, I'm getting majority as take one more example, so we'll take one, not a problem, not to worry. Alright, I'll take I'll try to do this as quickly as possible. It's a little lengthy one. So you can take any of these, what do we call? So yes, hold on. Okay, you can take any of these, what we generally call as, just move this so you can. Okay, I think some slide issues. I'll just try moving this. If you, I hope hopefully this helps the screen to be visible better. Okay, yeah, perfect. Now let's take this scenario. Let's start from here. Now this is our string. All right. Since this is our string, I'm going to start from first. First character, generally consider it as 0. Don't even worry about it. First character is always 0. After that, I have A. Is A my first character? No. So again 0. Next I have O. Is O my first character? No. Again 0. Next I have B. Is B my first character? I should have made one change. Everything should have been lowercase, so it'll be easier to understand. So please consider everything as lowercase here. I know I've made some characters as uppercase, but consider that we are ignoring the cases here. So I hope you guys can do that. Consider that we are ignoring the cases. Now B. Did we have B anywhere before? Yes. Since we did, I'll say that this is the first character of the prefix. Then A. Do we have A here as the second character of that prefix? Yes. So I'll take it as 2. Do we have the next character B as the third character of the prefix? No. So I'll make it 0. Then we start with T. Is T the first character? No. Again, sorry. After that we have 0 because space there's nothing. After that, is T the first character? No. Is H the first character? No. Is E the first character? No. Now, what about B? Space is not there. What about B? B is the first character. So I'll consider B as 1. Next A. Is A the second character? Yes. So let's consider A as 2. So after considering A as 2 over here, I think I should have added spaces. It would have been better. But I hope at least it's clear. So R. Is R the third character? No. So let's make it 0. Then again B. Is B the first character? Yes. So 1. Followed by that. Is E the second character? No. 0. Is R the first character? No. Is space the first character? No. Is L, I, F, T, S? None of them are first characters until we reach B again. B is the first character, so I'll make it 1. A is the second character, I'll make it 2. Is R the third character? No. So we'll make it 0 again. Then until you reach B, everything else is 0. Until you reach the first character, everything else is 0. Once you reach the first character, you'll make it 1. And if it continues same as the prefix, we'll continue ahead here. That's the basic idea. I hope this is simple and easy. Alright, so take this final example. Let's take this final example. We'll take one last case. Now S is the first character. First character is always 0 because it is itself the first character. So no need to point whether it's prefix or not. What about E? It's not the first character. A is not the first character. Now what should I write for S here? Now this is where I will ask you guys. Let's see if we can get it correct. Let's see if we can solve it right. Absolutely right. It is the first character. Since it is the first character, we're supposed to have this as 1. Absolutely right. What about H? Should I make it 1 or 0 now? Is H the second character of our prefix? Absolutely no. So we'll make it 0. Everything else is 0 until we reach one more. S. So here again, since you're reaching S, again start with 1. But O is not the second character. So let's make 0s itself and again start with S. Now S, E, A, S, H are here together. If you guys observe, S, E, A, S, H is here. Same prefix is available here. But after S, H, here you have E, here you have O. So 5 characters are repeated from the start. So I'll take 1, 2, 3, 4 and 5 here. After that, everything else will be 0 because none of them are the first character. So this is how it works. I hope now it is very, very clear. I hope it is very, very clear now. If it is clear, shall we go ahead with this example and try to see or try to learn how exactly our algorithm works? Perfect. Glad that it's clear. Glad that it's clear. I hope it's clear for everyone. I really hope it's not difficult because we've taken a lot of different examples, at least 3 examples for us to learn very, very well. Now, take this scenario, guys. The first thing, we're going to compare first character and first character. Are they equal? When we compare first and first character, I think this arrow mark is too big. I'll just use this. Perfect. Let's compare first and first character. Are they equal? Absolutely no. Since they are not equal, you have to move. I have one question. What we have to find? See, at Krishna's question, we need to find if this particular pattern is available in this string or not. We have to find out if this pattern is available in this string or not in the most time efficient manner. That's the idea. So let's go ahead here. Now, let's start with this sub sequence string or pattern or whatever. No, it's not longest substring. It's not longest substring. You're just trying to find if this substring is present in this string. We're just trying to find if this substring is present in the string. If you remember, what was our initial problem that we wanted to solve? Find rotations, right? If I had rotation, then I need to search something like IONROTA, for example. This is what I need to search here. I may need to search a lot of times. To avoid searching a lot of times, we are reducing the time complexity. We are reducing the amount of time taken by using this KMP method. Initially, we are creating this particular LPS. Now, to create LPS, you need to go through each character. You need to go through basically each character here. To go through each character, how many? Let's say we have M characters here. Let's say M characters here. I think I should have taken larger size over there. So I'll just make one small change. Kindly hold on, guys. Probably just a few seconds. Perfect. So let's take this. Now let's say this is M and let's say this is N characters long. So if the length of this is N and if the length of this is M, initially to find, I'll just write here M and N. Initially to find the LPS, I need to go through the entire pattern once. Since I need to go through entire pattern once, I'm going to say to find LPS, longest prefix subsequence. This is our pre-processing work. We are not even started. We haven't even started our algorithm. This is our pre-processing work, which takes M length. I have one question. First, we need to find the first letter and then we go for next letter until final letter. That's the general logic. That is the naive method. We're going to make some small changes here. Okay, I'll explain. Now, first, let's compare first two characters. Are they equal? Sorry, guys. Are they equal? They are not. Since they are not equal, what is the LPS value of this first character? 0. Since it is 0, you need to move 0 plus 1 ahead. Whatever is the LPS value, we need to move 1 extra ahead of it. That's all. That's the idea. Now, let's take a look at this. Here is the first character equal. Yes. Let's take the second character. Is the second character equal? No. Since second character is not equal, what is the value of second character here? 0. Since second character is not equal, I need to move only 0 plus 1. Only 1 length ahead. If I'm moving 1 length ahead every time, how does it make this algorithm better than the previous algorithm? How does it make our current algorithm better than let's say the previous algorithm, which was naive learning, naive based approach or brute force approach? Let's see. Now, are the first characters equal? No. So again, I'll move this by 1. Why by 1? Because since the first characters are not equal, what's the LPS value of the first character? 0. Since LPS value of first character is 0, I'll move 0 plus 1. That's the idea. Now, again, first characters are not equal, so move LPS of that character plus 1. This is where your program starts to be very, very interesting. Is the first character equal? Yes. Is the second character equal? Yes. Is the third character equal? Yes. Is the fourth character equal? Yes. Is the fifth character equal? Yes. Is the sixth character equal? No. Till fifth character it is equal. Since it is equal till fifth character, we need to move these many characters. We need to somehow move, let's say, something like 3 characters. Let's see what exactly we need to do here. What is the number of characters we need to move? If it is 0, we just move by 1. Please note, if it is 0, we just move by 1. Since it is 3 here, I need to move by some amount of characters to make sure that my algorithm works fine now. So let's see what exactly we're going to do here. This is where your algorithm starts to be different. This is where your algorithm ends up being very, very different. In this case, since B and C are not equal here, in our case, since let me just remove this, since till here it is equal, from B and C till it's not, since it's not equal in this scenario, we have a we have a mismatch here. So in that case, backtrack once, go one step behind. When you go one step behind, what is the value of the previous case? If you have gone through a certain set of characters, what's the value of the previous LPS, or what's the LPS of J minus 1? Just remember, guys, if you're comparing J and they are not equal, you have stopped here. Since you have stopped here, you need to continue from here. So how am I going to continue from here? I need to move in such a way that I should end up at the start of this sequence, because this is the next subsequence. We have already compared B and B. We know they are not, we know this is not the starting element. Starting element was A. Next I should move should not be here, because we definitely know A and B are not equal. Next I should move is the next place where A comes up, is the next character, next prefix subsequence of A here. So to ensure that we are going through to the next prefix subsequence of A, we're going to move accordingly till here. That is what we'll do. Again, when we do this, we will be able to reach the exact character where A begins again. Since we reach the exact character where A begins again, you can directly compare from here. Let's say even here something is wrong. Let's assume instead of this last A or something else was there. So you guys can again perform the movement directly all the way to the next A. That's the idea. Yes, this is string rotation problem itself. But for us to perform string rotation, we need to first learn and understand KMP algorithm. That's why we are solving, or we are learning KMP algorithm in short. And once we have done this, we'll immediately go for our problem. So this is the basic idea of KMP algorithm. Every time you move in such a way that you get to realize, if, see, here the characters are not equal. Since they are not equal, move by one. Here the characters are equal. So keep moving until you find another subsequence. If you don't find a subsequence, you have to move one element at a time. Please note, if you don't find a subsequence, you have to move one element at a time. If you do find a subsequence, however, in this case, we are finding a subsequence. Since we are finding a subsequence here, we're going to move all the way until the next time we find the start of the subsequence. That is what we're going to do. This is the exact logic we're going to apply. This is the exact thing we're going to do, because here the value is 3. According to the value as 3, we're going to go ahead and move 3 minus 1. 3 minus 1 is 2. So let's move ahead 1 and 2. 2 steps done. Let's go ahead all the way over here. That's it. Now we can search. So this is the basic idea or algorithm. Now let us quickly take this up. So what we're going to do here is, if you guys remember our problem, if you guys remember our program, our logic is that we have similarly here a string like this. Let's say this is what we have, and what I want to search is this. Let's say this is what I want to search. I can get it from here. Since I'm getting it from here, I need to keep moving from here to here to here to here. In our case, there is no repetitions. You guys can see that there's only one repetition here, that is T here. But in some other case, if we don't take rotation, if we take something else where there are subsequences which repeat, in that case, KMP algorithm is going to do better. Since most people solve by, again remember, since most people solve by big of n square itself, whether you use this method regularly as it is, or whether you use rotation of string manually, either way it is big of n square. To avoid that, we're going to make sure that it's only going to be big O of 2n at maximum using this logic. That's what we're going to do. Think about this, guys. In our case, at maximum, how many steps do we need to take to find LPS of this? To find LPS of this, I need to take n steps. And then to compare here, there will be a maximum of only n steps itself. N plus n, 2n here. Because the length of the string is 2n. Sorry guys, the length of the string is 2n. So maximum 2n comparisons will be there. Since 2n comparisons will be there at maximum with n, you can just say big O of 2n plus n. That's going to be 3n, which is pretty close to n when you take large amount of n values. So that's why we generally assume it as big O of n, but technically it is not. So let's quickly do this first algorithm, that is KMP algorithm, without any delay. Now, here's the first thing we need to do in order to implement KMP algorithm. We need to send two strings over here within, let's say, something like KMP algorithm. Let's create a function called int KMP. KMP algorithm will return either, let's just assume we return 1 or 0. If you want, you can even return in which index it starts from or something like that if you really want. But we don't want to do that. We only want to solve our current problem. We're going to take string str1, or I'll take string text and string pattern, because we generally search for pattern within a string. Pattern is the smaller string, text is the larger string. We search for the pattern within the text. That's the whole idea. So we're sending text as well as pattern. We are receiving text as well as pattern here. So let us first calculate the length of the text. So I'll take length of the text as int n equals, or let's say text length, or text length equals text dot size. Done. Let's also take int, let's say for instance, pattern length equals pattern dot size. Done. We've taken the lengths of them. We've got the length. Now, once we have got the length here, so the next thing we need to do, guys, kindly hold on for just a second. Alright, so let's go ahead and try this out. Now that we have done this, one of our first thing we need to do, one of our first scenario we need to do, always when it comes down to interviews, what if there is no pattern? What if the size of the pattern is 0 or something like that? That is something we're going to have to find out here itself, because we should only check for rotations if the string are equal in length. If the strings are not equal in length, there's no point in checking rotations as well. So you can check something like if string1 dot size is equal to string2 dot size. Only when the sizes are equal, you can perform this. Otherwise, you can print 0. All that we are doing here is printing 1 if there are rotations and printing 0 if there are not rotations. Or you can also print something like no rotation if there are not rotation, or return rotation if there are rotation. So it's completely our choice. That's something we can do. If they're not of equal size, we don't even have to spend much time. We don't even have to go ahead. In what way does this help? For those test cases, our program will be faster, because if two strings are not in equal length, there will never be rotations. So that is basically what we are doing here. So we're going to send it to check rotations function. In check rotation function, I'm appending string1 to itself. Appending string1 to itself. Once done, you need to call the KMP function. Now, I don't think we have called it anywhere. Yes, no, we haven't. Alright. So we're going to call KMP function now. In KMP function, we're going to send string1 comma string2. The first string we're going to send is the text, which is string1, which is appended to itself. That is in what we are supposed to find. And string2 is the smaller string, that is this. This is string2. This is going to be string 1. We're going to search string 2 within string 1. To search string 2 within string 1, we're going to call KMP and we're going to get a value in return. So we'll return either 1 or 0. 1 if it is found, 0 if it is not found. If it returns 1, we'll return rotation. Else we can return no rotation. So to find rotation or no rotation, to find if string 2 is a part of string 1 or not, what we are doing here is pretty simple. We're calling KMP function with the string 1 attached to itself because the rotation must be here. Immaterial, it must be here. So that's what we're doing here and we're calling KMP of it. That's it. Now in KMP, we're taking the text and the pattern. We're finding text length and pattern length. Now let's start our logic over here. Let's start our main program over here. So the first thing we need to do is a couple of scenarios. First thing, I need to create an array. I need to create an array that is called our, as we call, LPS array. So I'm just going to write here as int LPS of n plus 1. Or instead of n plus 1, I'll just take pattern length plus 1. So it is our choice to either take LPS of pattern or LPS of pattern plus 1. To make it easy, we can take pattern plus 1. One small value doesn't make much of a difference. Or we can take LPS of the value as it is directly. It's completely our choice, so not to worry about it. Alright. Now, let us start with this. Let us start with the basic idea. Now, here's the first thing we need to do. Initially, what I'm going to do, again, please remember this very, very clearly, guys. In this algorithm, I'll just point out very, very quickly so that we can just note this and point this before we start our main part of the program. I think some of you may end up being confused if we do this, like in this particular way, in this particular array. So I'm just going to make it a little easier for you guys. Don't worry, we're going to make it a little easier for you guys. Let's only take pattern and length. We need to create our own array, right? So that is called LPS. So I'm going to create a vector of it. It's completely your choice. You want to create a vector of it, you want to create an array of it. It's totally your choice. If you want to create an array, you can create an array. If you want to create a vector, you can create a vector. That's completely your choice. Really not much of a difference. We'll include a vector here as well. Now, in this vector of integer, where we call it as LPS, we need, let's say, m elements. And we're going to have to create our own separate function where we have to send the text and we have to create LPS. We're going to have to create a separate function. Now, please note, this is not a very small algorithm. This is sort of a lengthier algorithm compared to others because there's a lot of different things we need to do. There's a lot of different conditions. There's a lot of different cases we need to work with. But it's not too difficult. It's going to be pretty easy. So let's go ahead and let's take our, let's create LPS. And we're going to send, instead of this, I'll do one thing better. I'm going to create it an integer array as well. Again, up to your choice. You can even create a vector as I pointed out. And you can send, let's say, a reference of a vector. So in C++, for anyone, if you guys don't know this, just remember, you can send an array or anything you want. If you want to modify this array or vector here in a different function, like void create LPS of, let's say, string pattern and vector of int, instead of receiving it as a separate variable, instead of receiving it as a separate vector, you can receive it as a reference by using ampersand. So whenever you use ampersand, it's going to receive it as a reference of the current vector. That will make sure that any modification done here will also reflect in this vector. That's basically what we're doing here. Now, let us start with the basics. Let's start with the very, very basics. LPS of 0 is what? As we know, that is 0. That we set it right here. No doubt about it. Once it is done, we need to find a couple of things. We need to find the length because initially I'll keep length as 0 because we need to find length of the longest prefix subsequence. For that, I'm going to use a variable called len over here. And for us to go through, we need to go through first index. We don't need to go through index 0 because for index 0, you have already calculated LPS of 0 is 0. So we need to start from LPS of 1. So I'm going to write int I equals 1. That is the index we are starting from. And here's what we're going to do. We're going to repeat this until we reach pattern.length. So while I less than pattern.length. So guys, as long as I is less than pattern.length, we're going to have to perform a couple of things. So first thing, what I'm going to check here is if, please note this, pattern of I is equal to pattern of length. What is our initial length value? Length value is 0. I value is 1. If our first scenario here, if pattern of I, let's say I is 1, is pattern of I is equal to pattern of length? No. Since it is not equal to it, we need to use a separate function, separate condition. So we need to use something like else. So there are two scenarios we'll do here. If they are equal, else they are not equal. Now, let's start with if they are equal. If they are equal, what do? I increase length. Think of this. I'm starting from here. This is my current index I. Is pattern of I equal to pattern of length? I is 2, length is 0. Pattern of I, sorry guys, I'll do one little thing. I'll just move these here and I'll just write indices for you guys very, very quickly. Let's take 0, 1, 2, 3, 4, 5, and 6. Is pattern of I equal to pattern of length? Absolutely yes. Since pattern of I and pattern of length are equal, I'll increase I and I'll increase length, and we need to compare that up next. So in this case, I'm going to go ahead, increase I and increase length. I'll increase length and I'll increase I. But before increasing I, please remember, before increasing I need to take LPS of I is equal to length. If you guys observe here, since this is our first character, if you guys see, this is the first character. Since it's the first character, length is initially 0. So I'll increase length to 1 and store it in LPS of I. This is our index I that we are comparing with index length. So before we make sure that they're equal, first thing I'll do here is increase length, and since length is pointing to index 1, whatever is the value of that length, or whatever is the value of that index 1, I'm going to store it here. Done. Now after that is done, I'll move I, I'll move length. Length is already moved, I'll move I. Now length and I we compare again. Are they equal? Yes. Since they're equal, I'll move length, take the index of whatever is the value of length, I'll copy it here. Done. After that, I'll move I. So this is what we're doing over here. Even here, if you guys observe, A and A are equal. Since A and A are equal, whatever is length will increase it, that becomes index 3. So this is the third character. Since it's the third character, now since LPS of I is calculated, let's increase I to next character. Now are they equal? No, they are not equal. Since they are not equal, we will go to else part. In else part, there are two conditions. One is if length is not equal to 0, other is else. Because if you guys observe, in this case, what are we doing? When they are equal, when it is equal to the initial or initial prefix, we perform this. When it's not equal to initial prefix, we have two conditions. Either length is 0 or length is not equal to 0. When length is not equal to 0, let's say when length is not equal to 0, then I need to perform some operations here. I need to perform some different operations. First, let me point out what happens when length is equal to 0. If length is equal to 0, that means in this case, you're here, let's say I is here, sorry guys, I is here. Are these characters equal? No. Since they are not equal, length never increases. Since length never increases, length remains as 0. Since length remains as 0, we're gonna have to make sure that length in this case is basically same as it is. We just need to make sure that in our case, we'll just write LPS of I, whatever it is equal to 0. After LPS of I is equal to 0, the next thing is just perform I plus plus, increase I. And since you have increased I, you need to directly like go to next iteration. You just need to directly go to next iteration. You don't need to go through any other thing. So you can directly use something like continue. Even if you don't use it's fine. That's basically all right. Now, what if length is not equal to 0? What if, on the other hand, this is your L value and this is your I value? This is your current I value. Now, in this case, we need to keep checking. We need to keep checking for every single scenario. Here, in this case, sorry guys, length will be here. Yeah. B, it is not equal to C. They are not equal. Since they are not equal, I need to keep reducing length one at a time. I need to keep reducing length one at a time and check. That is, I need to keep reducing length one at a time and check if they match. If they don't reduce length by 1, check if they match. If they don't reduce length by 1, check if they match. So this we need to keep on doing until we reach back to length as 0. This is because what if a prefix sequence continues? What if a sequence from here is continuing ahead? If it's continuing ahead, we need to make sure that I need to reduce length one at a time and check if C is somewhere existing before. If C is somewhere existing before, we need to do that. Like let's say for example A. Since A is here and A is here, since I know that A is existing here, I need to make sure that I know whether our current, let's say, case starts from here. So that is the basic idea. We just keep reducing length by 1 at a time. So I'm just going to write here, in this case, where is it? Here. Alright. Here I'll just write length equals LPS of length minus 1. We're going to reduce length 1 at a time. So here if you guys observe this, in this scenario, when length is not equal to 0, of course it's not equal to 0 in this case. So length will be equal to LPS of length minus 1. So length will directly go to index 1. And we're going to check if these are equal. Why am I checking if these are equal? Remember, we were currently in here. Now, if this is the case, if this is where we are, what was the previous character here? A. Since A was the previous character, L should go in such a index, L should go to such an index that A should be its previous character as well. So to do this, we reduce L to such a way that we reduce it to LPS of that whatever is length minus 1. Length is currently 3, LPS of L minus 1, sorry, length is currently 3, LPS of 2 is 1. So that is why we go to index 1. This will show us that if this is our second character, first character is exactly A. That's how it works. This is our advantage. So now with this example, you are able to see how it works. With this example, now we are able to see how exactly it works. This will help us to make sure that we are not going through too many loops. We have only one loop. Under one loop, we have multiple conditions. That's it. So after this is done, after we go back to, let's say, this previous condition, we just continue. For the same I, we have to repeat. For both of this, we have to repeat similarly. So that is exactly what we are basically doing here. So even here, you can basically write continue. So that anyway, it's gonna skip everything. It's completely our choice to whether write it or not. It truly doesn't make much of a difference. Once this is done, this is gonna return to us our LPS array. Now, just to check that it returns, you can also print here something like the entire LPS array and see whether it works. So I'm not sure where and all we may go wrong here. So I haven't returned anything here. I need to return something like let's say A or something like that. What are we returning here? Integer, right? So I'm just going to return something like 1 here. So let's see, we may go wrong somewhere in the program. We have done too many things over here. So I'm pretty sure something may have been missed out till now, as expected. Let's see. Where have we missed out um, some basic system, basic output? It says that no operator for this particular symbol. Let's go all the way up. It says there's no particular operator found for double left shift symbol. There's no operator found for C out is what it says. I think I've made a mistake anywhere here. I should include IO stream is correct. Using namespace standard is correct. So it says that I have one question. Can I use pattern in string directly in Python? Okay, I just saw the question. So what happens when you use patterns directly is that they don't use KMP algorithm. You can use them. There's no doubt about it. But as I pointed out, the logic is that you have big of n square. If you really have one program, something like this, string rotation, 30 minutes, 45 minutes programs like this, and only one program is there to solve generally, you can then in such cases implement. Right now we are learning it. Since we are learning it, we are taking a little bit extra time for ourselves to, let's say, implement it, ourselves to, let's say, work it through, since we are basically learning it from scratch. But once you have already known this, once you have already know this, let's say, algorithm, it really shouldn't be so difficult in our case. That's the basic idea. I hope that gives a simple scenario. Now let's see where exactly we are going wrong here. Hash include IO stream. I'm not sure if I've missed if some file is deleted by chance or something like that. I'm really not sure. Let me just check this out. Okay, of course. Let's take this for I in sorry, I equals, or I'll just take I int I equals 0, I less than lps dot size I plus plus, and I'm just gonna have to print lps of I. Let's try compiling this. Perfect. Let's try running this, because we can't print the entire, like, how do I say, vector as it is. So I'll take rotation and rotation. It's supposed to give us let's say the LPS array. It's supposed to give us the LPS array. I should have specified the size. See guys, there's one problem. I'm directly using LPS of I here. I'm directly using LPS of I without specifying the size of our LPS array. So if I want to directly use I, then it's becoming a problem. If you directly want to use an array I, you really need to specify the size. Otherwise, you need to, on the other hand, this is the parameter I'm sending with the object. This is the object, I'm sending this as the parameter. So if you directly send, let's say, the size here is pattern length. You can directly send the size, or you have to use pushback function. Here I'm not using pushback function. I'm directly using LPS of I. So either that, or I have to use pushback individually and do this. So let's give this a quick try. Let's see what exactly happens. Now we can get to see our entire LPS is full of zeros. Now that's not supposed to be the case, right? Since there are 6 elements, you can see here 1, 2, 3, 4, 5, 6, 7, 8. 8 elements are there. So our LPS array clearly has 8 elements, no doubt about it. But the problem here is, even though we have created our LPS array of, let's say, exactly 8 elements, and we are sending it over here to, let's say, create LPS by sending our pattern string and our vector, let's say, LPS. Somehow we are getting here that the entire LPS array is filled with zeros. Because do we have R repeating anywhere? Do we have the first character repeating anywhere? Absolutely none. Now let's try a different scenario. I'll take rotate. Now if you observe, for first 6 characters rotate, there's no repetition. For the next 6 characters, you have these repetitions. You are getting the LPS array perfectly here. Now once you've got the LPS array, all you need to do is perform the search of LPS array here. This is the easier part. It's very easy. So we just need to go through the entire text. So I need to create a integer I equals 0 and while I less than text length. As long as we are going through the text length, as long as we are going through one character at a time of the text. Now I need one more index, that is j as well. I forgot to inform you guys, because we have, if you guys observe here, I need one particular index for this array and another particular index for my text array. Since I need two indices, one for my pattern array, one for my text array, I'm just basically using I and j. Remember, I will be for text array, j will be for pattern array. That's it. So let's start this. I need to check if my pattern array index value is equal to my text array index value. So this I need to keep on repeating again. So I'll just write here, if pattern of I is equal to text of I. If they are equal, all that I'm going to do here is just perform I plus plus and j plus plus. That's it. If they are equal, I go to next character. Let's say, for example, sorry guys, kindly hold on. Yeah, perfect. So let's say if they're equal. So guys, what happened? Yeah. Okay, I think this is where I went wrong. All right. So let's say if they are equal, for instance, here this is I, this is j. Sorry, this is I for our text is here I, the pattern here is j. So if text of I is equal to pattern of j, then I'll increase the I value. Sorry guys, I'll increase the I value for text and I'll increase the j value for pattern. That's what we do, right? If they are equal, I'll increase I, I'll increase j. That's all. What if they are not equal? Now this scenario, what if they are not equal? If they are not equal, we're going to have multiple scenarios. We're going to have two scenarios. One scenario is if j is equal to what are we store pattern length? Path length. If j is equal to path length, if you keep on increasing, this till a point of time where the index j will keep on going until one point of time where I and j are not equal, where I and let's say j are not equal. At one point of time when I and j are not equal, when you increase I, see here I and j are equal, right? This is I, this is j. Since I and j are equal, j will increase by 1. And what will j become? J will become size of this entire array. Because j was initially 0, 1, 2, 3, 4, 5, 6. And once j increases, j becomes 7. Once j becomes equal to the size of our pattern or length of our pattern, that means we have found the entire like substring over here. Since we have found the entire substring, what are we supposed to return? We are supposed to return, let's say 1 here. That's it. If we have found it, we return 1. That's it. End of it. Now, if we haven't found it, now after increasing, if they are equal, we increase I and j, and then we search if j has reached pattern length. On the other hand, if j has not reached pattern length, that means there's a possible chance that pattern of j might not be equal to text of I. Here, if you guys observe in this scenario, we have to go through all test cases, right? That's basically what we are doing here. Here, pattern of I, is it pattern of j, is it equal to text of I? No, they are not equal. Since they are not equal, we need to write this particular condition, that is else if, let me just quickly write it, else if pattern of j, pattern of sorry guys, here again I've used pattern of I. We shouldn't make such mistakes. I shouldn't make such mistakes. So pattern of j is not equal to text of I. If it's not equal to it, then I have to move according to my LPS array. That's the idea. And to move according to my LPS array, I need to also make sure that I have not reached the end of my string. I need to also ensure that one more test case is that I have not reached the end of the string where I and j are here. If that is the case, then no point in going further. So that is one more case. I is less than text length. This is our entire code. That's it. In this else if case, we just need to write a couple of simple scenarios. Here, if j is equal to 0, if our pattern and text are not equal, there are again two test cases here. Let me quickly write them down for you guys to observe. If we are in the first scenario where j is 0, j is the first character of our pattern. If first character of our pattern itself is not matching, then we only move it by 1. So that means we are only performing here j plus plus. That's it. That's all we're gonna do. Simple logic. Sorry, not j plus plus. We're gonna have to move our string because j is the first character here. This is I. J represents character of pattern. I represents character of string. Since I represents character of string, I need to move I here so that I'm comparing to the next I value. That's basically what we're doing. So let's quickly do this step as well. Otherwise, else, what was the scenario that we did? We just write j equals LPS of length minus 1. Now, what is this length? We haven't used length here. Now, sorry, j minus 1, our current index. So, if they are equal in some other scenario, like let's say this, they are no longer equal. Since they are no longer equal, what do I need to do? My j value becomes whatever is this LPS of j minus 1. So, j should point over from here. That is, we start from here. That's the basic idea. This is the basic idea and the basic program for us to work through and solve this. So by the end, if we don't get anything, we basically return 0. Let's give this a try very quickly. We have taken, I think, a fair amount of minutes on top of the session here. Let's quickly give this a try. I'll take rotation. I'll take rotation row here. It says it's a rotation. The output comes up as rotation. Now let's try one more scenario. I'll take rotation and rotating. Now it says there's no rotation. So our program works perfectly in all these scenarios. So this is the basic idea on how you get to find out if a string is a rotation of another string. Of course, the length is longer, it's lengthier, but especially when you get these kind of programs. What I mean to say is when you get these kind of programs in interviews, the idea is that you need to find out the most efficient time complexity. And if you're able to find the most efficient time complexity, one method we have already done it. We've already done one method where you just need to use substring function directly. It's just one line of code. But this, on the other hand, is nearly 40 lines of code. If you know this algorithm and you're able to write it down in a shorter amount of time, then you'll definitely be able to easily work through this. And if you do this, you will have a better time complexity than most others who are solving the exact same problem. Now, isn't that an advantage? I have one question. What is vectors? So the vectors are basically arrays itself, but they are resizable, which means you can change the size of vectors as you want. So there's literally no difference between vectors and arrays, except for the fact that for arrays you need to manually change size by using malloc, calloc and everything. For vectors, you don't have to worry about that. So with this, I just want to point out one major thing to everyone. No matter what kind of question you get, always try to learn the most time efficient algorithms, because they will definitely help. So yes, the most time efficient algorithms will definitely help us out a lot, as they are one of the best ways for us to make sure that we are a step ahead of all the other programmers. So we've just shared the link for this algorithm. If you want to go through this, you can give this a try. The time complexity is nearly like exponentially lower than the other method. Isn't that amazing compared to what others may have or others may do? Of course it is. But it comes with a one problem, that is the time required to implement it, because the number of steps you need to remember and implement are basically somewhere around 50 lines of code. Half of them are brackets anyway, so you can say somewhere around 30 lines, 20-25 lines of code is what you need to know. So if you know that, if you remember this, if you try to take one or two examples with this, it'll be very, very easy for you guys to work through. So make sure you guys try as many programs as possible. If this is your first session that you're going through our YouTube lecture series, you can definitely go through more of our videos which are already available in playlists for aptitude as well as technical, and give them a check. I have one question. What is the limitation of vectors? See, vector, most of the times we create it in such a way that we don't give it a size. So every time you add one more element, size of the vector keeps on increasing. Like if the size of the vector is this much, after adding every element, the size keeps on increasing. Since size keeps on getting added after you add each element, that is a little time consuming. That takes a little more effort. If you create a vector of fixed size earlier on, then that's not a problem. But then again, what's the point in creating a vector of fixed size? Because you can create an array of fixed size. You only do vectors when you don't know the size. That is where we use them. So that is the major difference. Arrays you can use if you know the size. Vectors you can use if you don't know the size, because you may need to increase and decrease, and you don't have to use malloc and kelloc. So that is where you can see what is more advantageous. So with this, I hope you guys had a fun time going through this program. I'm glad that you guys are sticking out through the sessions till past 10:30 p.m. as well. Very encouraging to see that. So good luck with your interviews. We'll catch up very soon again in the next sessions. Until then, have a good night and take care, guys.